Hello everyone, welcome to IIT and Gate classes. This is lecture 1 on compiler design. Okay, so today we are going to start compiler design topic. Okay, and it is our first lecture on compiler design. Okay, so the very first and the very basic question which will come to our mind is what exactly is a compiler? So in one line, I can say compiler is nothing but a language translator. Okay, so compiler is nothing but a language translator. What exactly is language translator? See, I can give you one example. For example, see here, uh, input to compiler will be one language, say L1, and output of compiler will be another language, say L2. Now this L1 and L2 can be any languages, or you can say any computer languages or any programming languages. Okay, so we can give here one high level language, and we can get output as also another high level language. So high level language 1 can be input, high level language 2 can be output, and so on. So it is not compulsion that compiler is converting high level language to low level language. Okay, it can convert one high level language to another high level language also. But generally, okay, what can we say? Generally what happen is input to compiler is a high level language, and output of compiler is assembly language. Okay, assembly language code, extension of assembly language code is .asm, so we are writing asm. Okay, so generally, or in most of the cases, high level language is converted to assembly language. Then this assembly language code is given to assembler. This assembly language code is given as input to assembler. Okay, and assembler will give output as machine code. Okay, and to this machine code, user will give some input and it will receive some output. Okay, so why exactly we are making programs? To give some input and to get some output. That means input is converted to output. This is the basic aim of writing program na. So the aim of writing program is fulfilled in the last step only. Okay, so firstly, high level language program is given to compiler. We will get assembly language code. This assembly language code will be given to assembler. We will get machine code, and to this machine code we will give some input and receive some output. So there, so total three stages entire work is done. Okay, so what are the three stages? Compilation, then assembler, and then input, and then output. Okay, so I hope I have made the point clear to all of you. Please try to note it down, and I am jumping to next slide. Okay, let me put everything on one slide so that you can note it down properly. Okay, so what exactly is compiler? In one line we can say compiler is nothing but a language translator. So it can convert one language into another language, or more precisely, it can convert one programming language into another programming language. Okay, that is the basic aim of compiler. Okay, yeah, so please note it down. I'm jumping to next slide. Now next is steps involved in program execution. Okay, so whenever program is executed, what are the basic steps involved in it? So first is, see, we write a source code. Okay, so extension of source code can be .c, okay, .java, and so on. But according to GATE or other competitive exam, C language is in the syllabus of most of the competitive exams. So I'm taking example of C language. So source code is written in C language. So extension will be .c. It is given as input to preprocessor. Preprocessor will give us output as pure high level language program or modified source code. What is preprocessor? I think you already know. Preprocessor, say file inclusion, okay, file inclusion, macro, okay, these are two preprocessor directives. Okay, macro, yeah, file inclusion is what? Hash include. We write na hash include stdio.h and so on. Macro is hash define, like we write hash define and 10 and so on. So wherever we have written n in the program, that will be replaced by 10 before compilation. Okay, so this is known as macro template. This is known as macro expansion. This is what? Macro template, and this is what? Macro expansion. Okay, so if you do not know about them, please do not worry. You will study all these things in C language course. Okay, in C language, you will study all these things. Okay, but I think you already know, and I'm just giving you hint. We write na hash include stdio.h hash include conio.h, whatever header file we have included in our program. That means what, that file will be pasted as it is in our program. Okay, so whenever we write hash include stdio.h, then stdio.h header file will be pasted in our program. Okay, of course we are not able to see it, that is logically pasted. Okay, and macro is hash define n10. So wherever we have written n in the program, that will be replaced by 10. So before compilation, macro template will be replaced by macro expansion. Why before compilation? See, we are saying here na preprocessors. That means what? Before processing, whatever thing is then, that is known as preprocessor. And properly we should say preprocessor directives. Directive means command. Okay, so those commands which are executed before compilation, that is known as, or before processing, that is known as preprocessor directive. Okay, so I hope I have made the point clear. So source code is given to preprocessor, and we get pure high level language program or modified source code. So for example, you have written 3-4 lines of code like void main int xyz and so on. You have written some code. So firstly, your stdio.h header file should be pasted in your program. Now see here carefully. Okay, let me show you here. Okay, so you have written a program like say void main. Okay, and you have done some coding, and here you have written hash include stdio.h. Okay, so before compilation, this file stdio.h, that should be pasted in your program. Okay, that should be pasted in your program, so that, okay, that should be pasted in your program, and then we will get a pure high level language code. Okay, or you may have used hash define n10, hash define n10. Now here you have written n, here you have written n. So all these n will be replaced by 10 before compilation. Okay, and this file will be pasted in your program. Then you will get, collectively you will get pure high level language code or modified source code, or modified source code. Okay, yeah, so I hope I have made the point clear. So now I think everything should be crystal clear to everybody. Please note it down carefully. Pause the video, note it down. Yeah, so we have got pure high level language programmer, modified source code. Now this pure high level language code, that will be given to compiler. Okay, this thing will be given to compiler, and compiler will give us assembly language file or assembly language code. Okay, compiler will convert high level language to assembly language, which I have already told you in the previous slide. Generally, or in most of the scenarios, this is done. That means high level language code is given to compiler, and it will give us assembly language code. So now more precisely, we should say pure high level language code should be given to compiler. And what is pure high level language code? After pre-processing, whatever we got, okay, that is pure high level language code. Yeah, so I hope I have made the point clear. Now assembly language code is given as input to assembler, and we will get what? We will get a relocatable machine code. Relocatable machine code means what? This machine code can be stored anywhere in the main memory, and still it can be executed. Relocatable means another name is position independent code. Position independent code means what? This code can be stored anywhere in the main memory, and still it can be executed. Okay, I'm not going into detail, but still, if you want me to give some example, then I will say like this. See, if you say mov, okay, in assembly language itself I am saying, if we say mov r0 comma 2000, so what does this mean? I am saying, okay, or let me say like this, mov r0 comma 5. So this means what? 5 should be stored in register r0. Okay, now and next line can be mov, okay, mov, or it should be like this, mvi. Okay, so actually it entirely depends on okay, so we should not dig deep into this, but I am just giving you some idea. mvi r0 comma 5, that means what? 5 should be stored in the r0, so it won't create any problem. Now if I say mov r0 comma 2000, this means what? From the location 2000 you are storing the value into r0. So in 2000 location say any data, whatever data is stored in 2000 location, that should be stored in register r0. You are saying like this. Now see here carefully. So what do you think? This is position independent code? No, it is not position independent code, because if you write the same code at some other location, then it may create some problem for us. Okay, so better is we should say, okay, we should say see, here we may get confused actually. For explaining this topic properly, you should have knowledge about architecture, so I'm not going into that detail. Let me give some another example. Okay, so let me say like this. See, a program is stored from some memory location, or it is stored somewhere in the memory. So at 2000 location we have written some code. Okay, at 2001 location we have again written something. Okay, and at 2002 we are saying jump to 2004 location. So 2003 and 2004. So you are saying that at 2002 location you are saying jump to 2004. So like this, you will jump here. Okay, now if you have no if you do not have any idea about what I am saying, then please leave it. I'm just explaining relocatable machine code or position independent code. That's it. If you are not able to follow, just leave it. I'm just giving you small introduction. Okay, so at 2002 we have written jump 2004. So at 2004 location we will have some, you can say, some code, and we want to execute that. Okay, so what do you think? Is it position independent code? This is the simplest example which I'm giving. So please try to concentrate here. So what do you think? Is it position independent code? No, it is not position independent code, because if this entire code, is shifted to say some other location 6000, okay, so at 6000, 6001, then 6002, okay, yeah, at 6002 location, at 6002, what we have written? JMP 2004. So it will jump to again here. So I think you have got it now. Actually, it should jump to 6004. Here it should jump, but it has jumped here. So what I am doing, I am just saying you code should be stored at somewhere in the memory. So I have started storing code from location number 2000. So this is our code at 2000 location. There is some code. We are not concerned about it. 2001, we have some other code. Okay, at 2002 location, we have jumped 2004. So at 2002 location, whenever a computer will execute or processor will execute instruction at 2002 location, then it will jump to 2004 location. Okay, now if you copy this entire code to somewhere else in the memory, say I have shifted this code in place of storing from 2000, I am storing that code from 6000 location. Now we will have problem, because we have written jump 2004. So actually we should write jump 6004, but we have written only 2004 because entire code is copy pasted somewhere else in the memory. So it is not position independent code. So better we should write here, say we should write here in place of jump 2000, we should write here jump R1. So in R1 register we have some value, and here also we have to write jump R1 only, because entire code is copy pasted. Now the only thing is, in R1 register you have to change value from 2004 to 6004. That's it. Okay, so in that, this is if I go to more detail, then I will say that it is indirect addressing. So jump R1 means what? I am not jumping to R1, I am jumping to content of R1. Okay, so whatever value is stored in R1, I am jumping to that location. Okay, so it is indirect addressing mode. So indirect addressing mode is used for writing position independent code. So main application of indirect addressing is writing position independent codes. Okay, I hope I have made the point clear to all of you. Okay, so just by changing register value, we can shift entire code to some other location. That is the main advantage. This is known as position independent code. Okay, so assembler will give us relocatable machine code or position independent code. Now this machine code will be given as input to linker loader, and we will get target machine code. What exactly are linker loader? That is not required. Okay, because it is a basic course and I'm not going into detail of all these things. I'm just leaving it. In advanced course, I will of course teach you all these things. Okay, and then we will get a target machine code. Now this machine code, okay, please, first of all, please note it down carefully. and then I will jump to the next slide. Okay, please note it down carefully. Yeah, these things should be noted down, and this also please note it down. Okay, yeah, I hope you all have noted down all these things, and I'm jumping to next slide. So we have got till now what we have got. We have got target machine code. Now see in the next slide. To this target machine code, we will give some input and we will receive some output. So the three-stage work which I have shown you in abstracted manner, that is exactly done in the form like this. Okay, so now question arises, what are these things? Assembler, linker, loader, compiler, and so on. So in this particular course, we are not going to study about assembler, linker, loader, and so on, or preprocessor. We are just concentrating on compiler itself. Okay, so till now this is a black box for you. What exactly is compiler, what are its phases, and so on. So now I am going to explain it properly, what exactly is compiler. Okay, so yeah, so slowly I am going deep into the topic. Okay, so see here carefully. Now this entire thing, the black box which I have shown you as a compiler. Okay, now I am showing you in detailed manner what exactly are the phases of compiler, or how exactly compilation is done. Okay, so see here carefully. Okay, let me put everything on one side so that you can note it down properly. Okay, yeah, so pure high level language program, we have already got it from where? After preprocessing. Now this is given to compiler now. So this entire thing is compiler. Okay, let me show you. This entire thing is compiler. This is compiler. Okay, so compiler was black box for you. Now I have opened it for you so that you can see what are the phases of compiler. So total we have 6 phases in compilation. First is lexical analyzer. Lexical analyzer will produce output as a token. Now this token will be given as input to syntax analyzer. Syntax analyzer will produce parse tree. This parse tree will be given as input to semantic analyzer, and semantic analyzer will give us annotated parse tree. And this annotated parse tree will be given to intermediate code generator, and we will get intermediate code. There are lots and lots of forms of intermediate code. One of them is 3 address code, which I have shown you. And don't worry about it. I will show many intermediate codes to. I will show you many intermediate codes when I will jump to this phase properly. Okay. Yeah. So 3 address code is given as input to code optimizer. We will get optimized code, and then optimized code will be given to code generator, and we will finally get assembly language code, and that is nothing but your ASM file. Okay, assembly language file. Okay, so all these phases will interact with a special data structure called symbol table. Okay, and all these phases will also interact with a special you can say code, or you can say special software called error handler. Okay, yeah. So let me give you a small example. Okay, what exactly symbol table? Symbol table, you can say, is a data structure, which store. Okay, let me show you with another pen. Okay, so symbol table is nothing but a special data structure which store entire information, about variables. Okay, whatever you can say thing you have defined yourself, that for that thing, or you can say for that thing, a symbol table is used. Okay, for example, you have defined variables, okay, functions, and if object oriented programming, then class, object, etc. So for whatever thing you can give name, that thing will be stored, or for that thing entire information will be stored in the symbol table. So data structure, symbol table is a data structure which store entire information about variable, function, class, object, etc. So if you have knowledge about C language, then you should know what is scope of variable and so on, what is the data type of variable. So information about variable can be what? Its data type, its scope, its lifetime, its value, and so on. Okay, so all these things will be stored in the symbol table itself. Okay, function, what are the arguments of function, how many arguments are present, what is the return type of function, what is the name of function, and so on. Okay, so all these things will be stored in symbol table. So symbol table is a data structure. Roughly, you can think of it just like a table itself. You are saying a table. Okay, and symbol means what? Symbols which you are defining yourself. Okay, like name of variable you can give yourself. It's your own choice now. Whatever name you can give to variable, whatever name you can give to function, and so on. So compiler in advance do not know about them. Whatever name you can give, whatever name you want, you can give. So it's the duty of compiler to store entire information about that thing in symbol table. Okay, so I hope I have made the point clear what exactly is symbol table and what exactly is error handler. So see, while lexical analyzer, syntax analyzer, and so on, any phase can show error. So all these errors will be given to error handler, and error handler will show them on monitor. So you can think of error handler as a clerk. Okay, clerk in a bank. So these all are the customers. These all are the customers. So they will say, "Hello, error handler. I have some error." Like for example, syntax analyzer will give some syntax error. If you have knowledge about C language, then you can obviously say every statement should end with semicolon. So if semicolon is not present, then it is a syntax error. So syntax analyzer will find this error, like semicolon missing, and it will show to error and it will give message to error handler, "Hello, error handler, I have some error." So error handler will ask, "Okay, I have noted down this error." So okay, so first it will say, "Who has given the error?" Syntax analyzer will say, "I have given the error." Then error handler will say, "What is the error?" Then syntax analyzer will say, "Semicolon is missing." So error handler will note it down and it will show it on the monitor. Okay, that is the basic work of error handler. So error handler is a clerk, or you can say it is assistant to all these phases. These phases will just order handler, and error handler will follow their order and show the message on the screen or monitor. Okay, or whatever may be the error, that will be shown on monitor with the help of error handler only. Okay, so I hope I have made the point clear to all of you. Okay, now these four phases are known as front end or analysis part. Okay, these four phases: lexical analyzer, syntax analyzer, semantic analyzer, intermediate code generator. All these are known as front end or analysis part. Code optimizer and code generator, these are known as back end or synthesis part. Back end or synthesis part. Why synthesis part? Because their code is generated. Okay, and why analysis part? Because here analysis are done, whether the code is correct or not, and so on. Okay, so I hope I have made the point clear to all of you. Please note it down carefully, and I am jumping to next slide now. Okay, so these are the 6 phases of compiler. You have to remember all these phases, and don't worry about them, how to remember and so on. When we will dig deep into the topic, we will keep on saying lexical analyzer, syntax analyzer, semantic analyzer, so it will fit in your mind. Obviously, there is no problem at all. These are the just 6 phases. You can remember them. Okay, and what are their outputs? And there is no need to remember their output. Whenever we will start a particular phase, you will get proper idea about what exactly are these and so on. Okay, so now my duty is to show a small piece of code, or you can say, forget about piece of code, a small line, or you can say single line. I will try to compile it, and I will show all these phases in one single line. Okay, so I will compile one line and I will show you what exactly a token, what exactly is parse tree, and so on. Okay, yeah. So let me jump to the next slide. So the topic is introduction to various phases. Okay, so what are the various phases of compiler? I will try to show you with the help of, okay, with the help of just one line. Okay, so I will compile this line. I will compile this line, and the basic aim of compiling this line is to show you what exactly are tokens, what exactly are parse tree, and so on. Till now, you do not know about what exactly is token, parse tree, and so on. So let me show you something. Okay, so this first of all, first phase is what? Lexical analyzer. So this line, this piece of code, okay, semicolon should be present, otherwise it will be a syntax error. Okay, so let me write semicolon here. Yeah, now it is okay. So it will be given as input. Okay, it will be given as input to lexical analyzer. Okay, so lexical analyzer will produce as output token. What are the token for x? X is a name of variable. So it will give like this, id comma 1, like this. Okay, equal to is another token. It will show like this, equal to a is nothing but name of variable, so it will be shown like this, id comma 2. Then plus is a token like this. B is again you can say variable. Okay, then star, and then C is variable. Okay, and then semicolon is another token. So all these are token. X is a token, equal to is a token, A is a token, plus is token, B, star, C, semicolon. Each and everything is a token. Roughly I'm saying them as token. In detail I will jump into more detail in lexical analysis phase itself. So when I will jump to lexical analyzer, I will show you exactly what are these. Actually these are lexemes. Okay, and then for each lexeme, lexical analyzer produce output as a token. So don't worry about lexeme and so on. I'm just roughly saying them. These all are tokens. Okay, so what is this? ID means what? ID is identifier, and one means what? This is the, you can say, attribute value, or you can say the pointer to symbol table, or you can say it is the first entry in the symbol table. Okay, so here is I am designing a symbol table. Roughly I'm saying. So name of the literal is X. Okay, and it's you can say it will be stored at the first place. Okay, yeah, and then id2 means what? Name of variable is A, and it is stored at the second row of the table, of the symbol table. Okay, then is id3 na. So name of the variable is B, and it is stored at in the third row. Okay, or roughly you can say it is a row number. Yeah, and then we have C will be stored at fourth row in the symbol table. So this is your symbol table. Roughly I'm showing you. Okay, I'm not going into detail and all. I'm just showing you. X is the name of the variable, and it is stored at the first row. And A is the name of the variable, it is stored at second row, and so on. So these are the row number 1, 2, 3, 4. These are the row number. You can flip them also. Okay, 1, 2, 3, 4 can be stored here, and X, A, B, C can be stored here, and so on. I am just doing roughly. I'm just showing you. Okay, what about my assignment operator? This is an operator now, so it will not be stored in the symbol table because it is a standard thing. See, whenever we install compiler of C language, then obviously a compiler, installing compiler means what? It already know the rules and regulation of C language. So it already know it is assignment operator, it is plus operator, it is multiplication operator, it is semicolon, and so on. So all these will not be stored in symbol table. So symbol table will store all the information which is, you can say, all those names which are given by user itself. For example, name of variable, name of function, and so on. Okay, so yeah, so we have got tokens. So this is first token, second, third, fourth, fifth, sixth, seventh, eighth. Total 8 tokens we have got from lexical analyzer. Okay, so now these tokens will be given as input to syntax analyzer. Okay, these tokens will be given as input to syntax analyzer. So syntax analyzer need two things. First is the stream of tokens. This is stream of token. Okay, and the second is grammar. Grammar we have already studied in TOC. Okay, second is grammar, and grammar here will be S implies ID is equal to E. E implies E plus T or T. T implies T star F for F. F to ID. Okay, this is the grammar. So syntax analyzer, let me show you in the next slide so that you can get the proper idea. Syntax analyzer actually need two things. First thing is the tokens, and the second is grammar. Okay, so first is token, second is grammar. Both are given as input to syntax analyzer, and syntax analyzer will produce as output parse tree. Parse tree if syntax is correct, or if this string of token, if this string of tokens is generated from this grammar, then we will get parse tree. Otherwise it will give error message that there is some error. Okay, so if this string of token is can be generated from this grammar, then output will be parse tree. Otherwise error message will be shown. Yeah, so how parse tree will be generated, you already know in the TOC subject itself. So what is the string? Okay, id1 equal to id2 and so on. So x is equal to a plus b star c, na? And grammar is this. So what I will say, see, I will say, okay, so let me show you here. I will say S tends to id is equal to e. See here carefully. S tends to id is equal to e. This is the only production, na, starting from S. So you have to apply it blindly. I have applied it. Now what we want, x. So id should be replaced by x, na. So what I will write, I will say this id is nothing but your x itself. Okay, or your token was id comma 1, like this. Roughly I'm writing. Okay, so x is here. X is equal to what? X is equal to a plus b star c. So a plus b star c, so a plus b, so e plus t, na. So you should write e plus t. So of course I'm not going into detail, and you already know about how to write the how to make a parse tree or syntax tree. Okay, let me say it parse tree only. Syntax tree is different thing. Okay, so a parse tree for the grammar. Okay, for a string. Okay, so I'm writing a parse tree for your string. Okay, yeah. So id is equal to e plus t. Now this now this e should be replaced by what? This e should be replaced by t, and t by f by id. Okay, so okay, and if you remember, I have already told you, see this grammar carefully. Okay, in toc I have used this grammar many times. E implies e plus t, or t implies t star f, or f tends to id. In ambiguity also I have shown you. So please try to remember it. If you do not remember, please watch my toc lectures. I'm not going to repeat them again and again. I'm just making a parse tree. Okay, so just to save time, I'm just making parse tree in a faster manner. So please bear with me. Okay, so e will go to t, t will go to f will go to id. So this id will be what? X is equal to a, na. So this will be like a. Now this t will be replaced by t star f. Okay, now t to f, f to id. Id will be what? X is equal to a plus b star c, na. So f will be replaced by id. So id will be what? C here. So see carefully. X is equal to a plus b star c. We have got the string. Okay, yeah, and there should be semicolon also. I have forgot that. Sorry for that. id is equal to is semicolon. Id is equal to is semicolon. Okay, so if semicolon will be missing, then obviously error will be shown by compiler. Yeah, so we have got the parse tree. Okay, so this parse tree, you can imagine that this parse tree will be given as input to semantic analyzer. Okay, so syntax analyzer has given us parse tree. So I think till now there should be no problem to anybody. We have one line of code. It is given to lexical analyzer. Lexical analyzer has produced token. Now these tokens are given to syntax analyzer. Syntax analyzer need two things: string of uh, tokens and grammar. Okay, and it will produce as output parse tree. So we have got the parse tree now. See in the next slide, we have shown you parse tree. This parse tree will be given as input to semantic analyzer. Okay, so let me write here semantic analyzer. Yeah. So now what will be done? Now what will be done? Okay, so this semantic analyzer will produce as output annotated parse tree. Annotated parse tree. Annotated means labeled. Annotated parse tree means labeled. See, we have got parse tree. No doubt we have got the parse tree. So semantic analyzer will check whether this parse tree is meaningful or not. Parse tree is meaningful or not. Meaningful or not. Meaningful or not means what? It is correct or not. For example, see, we have written x is equal to a plus b star c. Now a data type is int, b data type is int, but c data type is float. So error should be shown, na, ki, how we are multiplying int and float and so on. Of course, typecasting can be done. So just ignore typecasting and so on. I'm just focusing. See, data type of every variable should be same. So if data type of one of the variable is different, then obviously error should be shown. And of course, you may argue that, sir, typecasting should be done and so on. So forget about that. I just want to show you something. That's why I'm saying. So I'm assuming that data type of every variable should be same. Okay. So if it is not same, then error should be shown by compiler. So how error will be shown? It will be done. So where error will be shown? This error will be shown by semantic analyzer. Okay, because the error is in the semantic or meaning. Okay, so see here, every variable is int, but what about this? This is float, so error should be shown. Okay, so this error will be given by semantic analyzer. So semantic analyzer will produce what? Annotated parse tree. Annotated means what? Labeled. Annotated means what? Labeled. Okay, labeled or decorated. Okay, so what exactly is labeled? So actually I'm not going into detail because I will show you all these things in subsequent classes. When we will jump to semantic analyzer, I will show you all these things, but I'm just giving you hint. Okay, so if you are not able to follow, please do not worry about it. Okay, so I will say here, okay, so I will say here, data type will be, say, see here, data type will be here, id. Okay, so x data type is int now, so here I will say it is int dot int. Okay, here also I will say it is integer, so here it will come as int, here it will come as int, here it will come as int. Now here this id data type is int, so this id data type is int. Now this id data type is float, so here we will get float, and here t data type of t will be what? Int multiplied by float. So this will give you some error message. Okay, so if you are not able to follow, then please leave it. I am not going into detail. I am just showing you some example that this is the annotation for labeling. So I will, for each node of parse tree will be labeled with some attribute. Okay, each node of parse tree, let me write it in a shortcut manner. Each node of parse tree will be labeled, each node of parse tree will be labeled with some attribute, labeled with some attribute. Okay, that attribute can be type, okay, or size and so on. So here we have used attribute type. Okay, so here attribute used is type, or you can say data type. So data type is int, so I have directly attached int, and here float and so on. Okay, so properly, if you write, if you want to write properly, then we should write t dot type is equal to int, but just to save the time I have not written, so because you will get unnecessary confusions. Okay, so just I'm writing here, so t dot type, actually we should write like this, t dot type is equal to int, like this. Okay, so I think it should be visible to you. If it is not visible, then let me write here, t dot type should be equal to int, like this. Okay, so properly, but I am not going into detail because don't worry about them. I will show you in proper detail once I will jump to semantic analyzer topic. Okay, yeah, so so I'm just focusing on basic introduction. Annotated means what? Label. So what exactly is labeling? I have shown you what exactly is labeling. Each node of parse tree will be labeled with some attribute. Okay, or we will attach each node with some attribute, and that attribute can be the type, size, etc. There are lots and lots of attributes, so we can attach, and even we can attach more than one attribute also. Okay, I will show you all these things in semantic analyzer topic. Okay, so finally, okay, so what about the type of this? Nah, we will get here confusion. Type, so t dot type will be what? Integer or float? So that will obviously create some problem. Of course, we have some rules and regulations. According to that rules, we write here what will be the type and so on. So I'm not going into detail of all these things. I'm just giving you small introduction. Labeling means what? We will attach each node, we will attach some attribute with each node of the parse tree. Okay, that is known as labeling. And we will attach what? Attribute. Okay, we will attach some attribute with each node of the parse tree, that is known as labeling. Okay, and how these are attached, how exactly their values is calculated, like attribute can be typed. So how can we say that this type of this is int, type of this is float, and so on? So there are some rules and regulations. We will, don't worry about them, we will jump into them once we start our topic, semantic analysis. Okay, so we have attached some attribute, we will calculate their values. Okay, and so if we have found some error, then that error will be shown by semantic analyzer, and it will be given to error handler, and error handler will say that we cannot multiply integer and float and so on. Okay, so I hope I have made the point clear. Roughly I'm saying all these things. Okay, roughly, just to give you some idea. That's it. So I'm not going into detail again and again, otherwise it will waste our time. Okay, so semantic analyzer thing is done. Now semantic analyzer will produce what? Annotated parse tree. Now this annotated parse tree will be given as input to what? Intermediate code generator. I am writing in shortcut manner, ICG, intermediate code generator. So intermediate code generator will give us what? 3 address code I have shown you. So there are lots and lots of intermediate code generation, intermediate code. There are lots of types of intermediate code, and I'm showing you just one, that is 3 address code. So let me give you some example of 3 address code. So here we have what? X is equal to A plus B star C, na? The line was what? X is equal to A plus B star C. Okay, everything is fit and fine till now. Semantic analyzer has found that everything is data type is also same, int, all are int and so on. Okay, so everything is fit and fine now. So this line is proper. Now it is given as input to intermediate code generation. Now intermediate code generation will give us what? So 3 address code. Now 3 address code means what? Each and every line should have 3 addresses. Here we have 4 addresses in this line. One line is having 4 addresses, na? X, A, B, C. So we want only 3 addresses, or you can say at most 3 addresses. 3 address code means what? At most 3 addresses. At most 3 addresses. Okay, so what can be the way? So I will write here T1 is equal to B star C. Okay, and please try to focus here. Okay, do not say first do A plus B. How I can do A plus B? Because first we have to do B star C, na? Because we are just following the rules of mathematics only. So I will say T1 is equal to B star C. Now T2 will be equal to A plus T1 and X will be equal to T2. That's it. So this is our 3 address code for what? For this line. Okay, yeah. So now this 3 address code will be given as input to code optimizer. Code optimizer will produce optimized code. So what can you think? Can we do some optimization here? Yes, of course we can do. See, we have written here A plus T1 is assigned to T2. So why you have written this? Can we directly write X is equal to A plus T1? Yes, of course we can write it. So this is the optimization which is done by code optimizer. Okay, so finally what we will get? We will say T1 is equal to B star C and X is equal to A plus T1. Directly you can write X is equal to A plus T1. So see here carefully, again I am repeating, here we have 3 addresses, here we have 3 addresses, here we have 2 addresses. No problem at all. I have already told you at most 3 addresses. So this is also correct. So this is written in 3 address code, and now by optimization we have got this thing. We have deleted this thing. Okay, yeah, because of obviously it is creating it is just wastage of time, na? So firstly you are assigning it to T2 and then T2 is assigned to X. Directly assign it to X. Okay, so this is code optimization. And then finally this optimized code will be given as input to what? Code generation, CG, and it will generate code. Okay, so code can be like this. So it can be like mul T comma B comma C. So B multiplied by C and it will be assigned to T. Okay, and finally we can have add X A T1. So A and T1 will be added and it will be stored to X like this. Okay, yeah. So finally we have got the assembly language code. So if you are able to follow 50, even 50%, na, then also it is fine to me, because I'm not going into details and I have not shown you what exactly is going to happen, because exact details will be shown whenever we will jump to each and every phase. Okay, so till now I have just given you a small introduction. So this was our line. It was given as input to lexical analyzer. We have got the token. Token was given to syntax analyzer. Syntax analyzer need 2 things, token as well as grammar. Now we have got the parse tree. Parse tree is given as input to semantic analyzer. Semantic analyzer will give us annotated parse tree. Annotated means labeled. Labeling, I have already shown you what exactly is labeling and so on. Okay, so the main function, let me show you one thing more. I'm not able to control myself. That's why I'm showing you one more thing. The main aim, you can say the main work of semantic analyzer, I am writing it in shortcut manner. The main aim of semantic analyzer is type checking. Type checking means what? Variable is defined before its use or not. Like you have written X is equal to A plus B star C. What if you have not written int C? You have not written like this. You have not defined C and still you are using it. So this error will be shown by Semantic Analyzer. This is nothing but type checking. Okay, so checking the type of variable, that is type checking. And here also integer is multiplied by float. How it is done? So again error will be shown. So this is nothing but type checking. Okay, and so on. So there are lots and lots of things which are done by Semantic Analyzer. Okay, so I hope I have made the point clear to all of you. Yeah. So this is done by Semantic Analyzer. Then annotated parse tree is given as input to intermediate code generation, and it will give us 3 address code. And this 3 address code will be given as input to code optimizer. We will get optimized code, and this optimized code will be given as input to code generation, and we will get the assembly language code. Okay, so I hope I have made the point clear to all of you. Yeah, please try to note it down carefully, and I am jumping to next slide now. Please note it down carefully. Okay, I am jumping to next slide now. Yeah. Yes, so finally, introduction to compiler is over. So this is your syllabus of compiler design subject. So first topic will be introduction to compiler. This we have already studied. Next will be, we will study lexical analysis. Then third topic will be syntax analysis. Syntax analysis, let me tell you one thing. This is heart of compiler. This is heart of compiler. Okay. And if you have studied properly syntax analysis, then mostly you know compiler design subject. Okay, so in GATE, NET, and so on, in every competitive exam, weightage is 70 to 80% questions of compiler design subject. 70 to 80% questions of compiler design subject will come from this phase only, that is syntax analysis. Okay, only 20% questions have been asked from introduction, lexical analysis, SDT, runtime environment, code optimization. Okay, so all these topics, total 5 topics, only 20% weightage, only one topic 70 to 80% weightage. So of course you should know that this is very, very important topic, and of course we will spend most of the time in this topic only, and this is the biggest topic of compiler design. Most probably we will spend 7 to 8 lectures on this topic only. Okay, 7 to 8 lectures on this single topic, and rest these topics will be covered in 3 to 4 lectures only. Okay, so I will need half lecture for lexical analyzer only, syntax data translation 1 or 2 lectures, runtime environment 1 lecture, code optimization 1 lecture. Okay, so I need very few lectures for at most 1 lecture for each and every topic, but syntax analysis we need 7 to 8 lectures. Of course it is a very big topic and it is heart of compiler, and most of the questions will come from this topic only. Okay, so please try to note it down carefully, the syllabus of your compiler design subject. Okay, and then, so now we are jumping to the second topic of your syllabus. Introduction to compiler design is completed. Second topic is lexical analysis. This is your second topic. So I think we should start this topic from the next class itself, because it was just basic introductory class. So from the next class itself, I will start your first phase, that is lexical analysis. And hopefully I will complete it in the half lecture only, and I will start the syntax analyzer itself in the second lecture also. Okay, yeah, thank you so much. Bye bye.